We continue our discussion of facility layout with a review of work centers. In the introduction, we described work center layout as a situation where similar equipment or functions are grouped together, such as all lathes in one area and all stamping machines in another. A part being worked on then travels according to the planned sequence of operations from work center to work center. The example shown is for a toy factory, where the following work centers might be found: shipping and receiving, plastic molding and stamping, metal forming, sewing, and painting. In this toy factory, the work centers perform all parts manufacture. The parts are then sent to assembly work center to an assembly work center, which may also be part of the larger production concern for assembly. One of the principles of good layout design is to place work centers with much inter-work center traffic next to each other. As an example, our textbook considers placing 8 work centers in a workspace space as shown. As a first approach, we assume equal workspaces of 40 feet by 40 feet for all work centers. The space that we have suits those dimensions. Now we need to find out how much and what type of traffic there is between work centers. This information is available for our prying minds. The transport is done by forklift truck, which carries one standard-sized crate per trip. It costs $1 per trip between adjacent work centers and $1 extra for any additional work centers negotiated. The expected loads between work centers for the first year of operation are tabulated in Exhibit 6A1. Available plant space is depicted in Exhibit 6A2. The top figure gives the annual number of trips between work centers. For example, there will be 125 trips between work center 3 and work center 6. That is in any direction. In this case, given that work center 3 is metal forming and work center 6 is large toy assembly, the bulk of movement will probably be from work center 3 to work center 6. The bottom figure we already know well from our previous slides. The 8 work centers are shown as being organized from top to bottom and from left to right as a first approach, which we have to optimize. We note that diagonal moves are permitted, and diagonally adjacent workspaces are considered neighboring on each other. So a trip between work center 1 and work center 2 will be a single trip. Likewise, a trip between work center 5 and work center 8 will also be a single trip. We now illustrate inter-work center flow in Exhibit 6A3. 2 slides back, we used the example of 125 trips between work centers 3 and 6, which is now shown here. Now we need to calculate the cost for the basic layout by multiplying the number of trips or loads with the inter-work center distances. The results is shown in Exhibit 6A4, which is a modified version of Exhibit 6A1. The calculations are shown on the next slide. The figures in Exhibit 6A4 is derived as follows. The annual material handling cost between work centers 1 and work centers 2 is $175. that is $1 times 175 moves. $60 between work centers 1 and 5, that is $2 times 30 moves. $60 between work centers 1 and 7, that is $3 times 20 moves. $240 between diagonal work centers 2 and 7, that is $3 times 80 moves. And so forth. Then one should search for better solutions that will reduce the costs. One can think that by moving work centers 1 and 6 closer together, one may reduce their inter-work center travel cost. But that will necessitate moving a number of other work centers as well, with unpredictable results. The next slide, Exhibit 6A5, shows the resultant layout, while Exhibit 6A6 shows the cost. Note the total cost is $262 greater than that of the initial solution, which was $3,474. Clearly, doubling the distance between work centers 6 and 7 accounted for the major part of the cost increase. This points out the fact that even in a small problem, it is rarely easy to decide the correct, obvious move on the basis of casual inspection. We tested only one, what we believed common sense approach to improving the cost outcome of the problem. One must understand that for our layout example, there are 8 faculty or 40,320 possible layout organizations. So we did not stand a chance of improving the situation using only heuristics. One can try different layouts solely on the basis of logical thinking and then calculating the cost. We have a feasible solution in Exhibit 6A7. In this case, the cost comes to $3,550, which is 2% higher than that of the original layout. One must of course understand that we here only base cost on transport costs. There might surely be other factors to consider. We would note first of all that our shipping and receiving work center is near the center of the factory, an arrangement that probably would not be acceptable. Also, the sewing workstation should most possibly not be placed next to the painting workstation, as sewing emits fine cloth-related particles. Placing the two toy assembly areas so far apart will most certainly not be optimal, as the two assembly workstations can share resources. An algorithm exists that can assist in this optimization. It was originally developed by Amor and Buffa. It is called Computerized Relative Allocation of Facilities Technique, or CRAFT. It is an improvement algorithm which starts with an initial layout, like our example, and improves the layout by interchanging the departments pairwise, so that the transport cost is minimized. The algorithm continues until not further interchanges are possible to reduce the transportation cost. The result given by CRAFT is not optimum in terms of minimum cost of transportation. But the result will be good and close to optimum in the majority of applications. CRAFT is thus mainly a heuristic algorithm. Because layout problems are essentially combinatorial in nature, the use of an efficient heuristic like craft is inevitable. There is an Excel add-in available for this purpose. Various videos on the use of the method is available on YouTube. An example YouTube link is provided. The following is one of the screens from this video showing craft at work. Sometimes it is even not possible to obtain or estimate the number of trips between workstations. In such situations, the techniques known as systematic layout planning, or SLP, can be used. This is based on the principle of developing a relationship chart to base the layout on. This technique is further discussed on the next slide and will be illustrated on the slide after that. From this chart, an activity relationship diagram is developed. This activity relationship diagram is then adjusted by trial and error until a satisfactory adjacency pattern is obtained. This pattern is then modified work center by work center to meet building space limitations. This technique is illustrated in Exhibit 6A8 on the next slide, with a simple 5-work center problem involving laying out a floor of a department store. The relationship chart, Table A, shows the relationship between departments. For example, the relationship of Department 2, that is the toy department, with Department 3, the wine department, is unimportant. Refer to Table C, the U. On the other hand, the toy department relationship with the camera department is seen to be important. Also, the reason for the importance of this relationship is attributed to the type of customers, see Table B. And the toy department's relationship with the candy department is seen to be absolutely necessary. Also, the reason for the importance of this relationship is attributed to the type of customer as well as the psychology of the situation. The toy department needs 400 square feet of area. From this, the layout designer creates an initial relationship diagram using the line codes from Table C. So the relationship between Department 1 and Department 4 is especially important. On the other hand, the relationship between Department 4 and Department 3 is unimportant. Based on these relationships, a first layout is attempted, without taking floor space into account. From all of this, the final layout is derived. This then ends session 4B on work centers.